Yes, thank you. So since December, I'm a full-time employee here at Sanoma. But before that, I was actually doing my internship, my master thesis internship here on the context-aware recommender systems, and that's what I'm going to talk about today. How it's used within Sanoma, what I propose to improve the recommendations, what results were there, and hopefully, if time permits, a little demo as well. So context-aware recommender systems, what are they? Well, recommender systems first is something that you encounter every day on the web, basically. Google, Amazon, all kind of stuff use recommendations. You see here items in web shops on Amazon, Netflix, movies, Twitter, people you might want to follow, items on the New York Times. It's all stuff that's recommended. So basically the purpose of a recommender system is to help you find items that you haven't encountered before. You can use search for that, of course, but to help you in a way that you don't really expect things to happen is where recommender systems are used for. And basically it's based on the behavior that you had beforehand. So based on your behavior, the system provides some items to you that might be of interest. Well, that's recommender systems, the traditional recommender systems. In Sanoma, they are used as well on stuff like .duck shop. On the left-hand side, you see VT Wonen in the web shop, product recommendations, but also items on, for instance, the Viva forum. That's all stuff where recommendation systems are used. So I propose to improve recommender systems by using context. Well, first we want to have a look at what context is then actually. So this is the formal definition that I used in my research. Context is any information that can be used to characterize the situation of an entity. Well, the next question is, of course, what's an entity? An entity is a person, place, or object that is considered to be relevant to the interaction between a user and an application, including the user and the application themselves. So basically anything that can be useful for a recommendation can be used in that recommender system to improve the recommendations if you save it and if you know it. So some examples of this are, for instance, stuff that can be quite easily deduced, stuff like the time of the day of the week. That's all, well, basically logged within Sanoma in the analytics system. We have a timestamp, so we can simply use this information in the recommendations. But we can also get more complex examples, for instance, when you use the location, the geolocation of a user, but also the device that a user is using. So is he on a mobile device, is he on a tablet, is he at home on a laptop, stuff like that. And you can even get more advanced, for instance, using weather APIs from the Weather Institute, combine it with location to get the weather for that user at a certain moment in time when he's accessing the system, and that might also be of interest. And even if you got more advanced sensors, you can use stuff like the mood that a certain user is in, or the company that the user has when he's accessing the system, for which I will show you an example in a minute. So why do we use context in recommender systems? Well, basically, it has been shown that context influences the behavior of consumers. That was already shown in offline behavior. Well, you can imagine that when a user is walking through a city center, when he's shopping, the weather around him is influencing his consumer behavior. So when it's raining, he's more likely to buy an umbrella, for instance. Very simple example. There was an offline commerce, but it's also been shown that the same holds in e-commerce, online commerce, and recommender systems with contextual information therefore show an increase in the effectiveness of those recommender systems. And effectiveness here basically means that more relevant items are recommended to the users. And in the end, the goal, of course, for instance, a company like Sanoma is to get more users to buy items because they encounter those items using the recommender system. And that's also a form of effectiveness of the recommender system, of course. So an example, for instance, like Netflix, their movies are recommended. Well, a simple recommender not using contextual information might show some recommendations like this, a very wide range of movies, Harry Potter, Wolf of Wall Street, Lord of the Rings, stuff like that. But then when we use contextual information, we can get more recommendations that are more tailored to a specific user. So for instance, there are two use cases. In one use case, a user is watching with his family, parents with kids. In the other use case, he's watching with friends, so all adults wanting some different movies. And the movies can then be, that are recommended at that moment by, for instance, Netflix, can then be more tailored to that situation. So for instance, when you're watching with family, it's more the kind of the Finding Nemo, Chronicles of Narnia, more the family movies tailored for that specific situation. And when you're watching with friends, it's more the movies that are more targeted at an older audience. So that's an example of how context can improve recommendations, how it's used. Let's have a look at how they're actually implemented in recommender systems in the technical sense. So traditional recommender systems, most recommender systems are based on the interactions between users and items. What this means is that there is a matrix that's accounted for showing users on the rows and items on the columns. You have some interactions, you have some empty spaces as you can see, and then the system tries to predict those empty spaces, comes up with a predicted value for the relevance of those items, and based on that can show items to a user. So this is the traditional recommender system, but when we want to include context, there are different approaches. We can, for instance, annotate items, say that some items are relevant in a certain context. That's, of course, a really simple approach to doing this. And the approach that's more getting more attention at the moment and that I'm used in my research is extending this two-dimensional matrix to a three-dimensional model, which then becomes a tensor as it's called. And here you can see again the users and the items on two different axes, but then we introduce a third dimension where the context is stored. And then we try to come up with an algorithm that takes into account all those three dimensions and fills the empty places that are also present in this model, just like the traditional approach. So that was the goal of my research. The research consisted of 6 different data sets collected within Sanoma. I used 3 algorithm classes for the ones involved in recommender systems. That's a nearest neighbor approach, a matrix factorization approach, and an approach that's less common but claims good effectiveness in this certain case, the sparse linear method. And then for each of these classes of algorithms, I used a context-unaware, so a variant that doesn't use contextual information, and a context-aware variant of the algorithms to compare the effectiveness of context in the recommendations. I used 4 different contexts, which was basically the hour of the day of the week, the location of the user, and the device that a user is using. And I used an open source toolkit, the CARS kit, which stands for Context-Aware Recommender Systems, to implement those algorithms. I made some modifications to make it more suitable for the use case here, the large data sets that we have, and I used that to do the comparison between the approaches. So the results were basically graphs like this, showing for an n, which is the length of the recommendations, the effectiveness of the recommender systems. You see as a metric, it's mean average precision, as it's called, which basically says the fraction of the items that are shown to user which are relevant. That's basically precision. So here you see that 2 out of the 4 items are relevant. That means that there's a precision of 0.5. However, we want to achieve facts like this, where the relevant items are higher in the list because users are more likely to click higher in the list. And that's what the mean average precision also takes into account. So the right-hand list actually gets a better value than the left-hand list. So what were the results? So then I won't bother you with all these kinds of graphs for all different algorithms and data sets, but the results were basically that each data set saw an improved result when using one of the contexts, and each context improved the results for one data set. Why do I tell you this in this way? Well, because it's very hard, it turned out, to predict which context actually improved the results for which data sets. So that was one of the limitations in the research, but in general we saw improvements of between 30 and 69% for each data set, so that's quite significant, quite good. And like I said, first there's an increase in revenue, which is of course relevant to a company like Sanoma. An increase in revenue is highly correlated with the increase in effectiveness, which basically means that better results are not because basically cheaper items are recommended and are more relevant to a user, but in general, if better items are recommended, then the revenue that can be created by using the recommender systems increase with the same amount. And like I said, predicting which context improved the results for which data sets turned out to be very hard. So that's a limitation that should be taken into account. There are some other limitations as well. I used this only in an offline setting, no online or A/B testing. That was basically due to the fact that the library that I used, the open source library, was not able to handle such large data sets, and the algorithms should be made scalable to be used in production before it can be used. And the limitation was that models, the recommender models are only trained once, not incrementally, which basically means that you have to train the model each time that you get an interaction, and of course in a production setting that wouldn't be very sufficient. So the takeaways then are that, well, in general, recommendations can be improved using context, which is a very good conclusion here, but well, like I said, thorough testing is required, as predicting results is very hard, and it is expected in general that revenue increases as well. So then I want to show you a little demo of what this looks like. Let's see if I can get that to work. Where is the mouse? Mouse there. Yeah. So here I have, is it big enough? Yeah. So it starts out with a data set, a training data set, which has these kinds of entries. So you see here a user ID, an item ID. Here you see there's a 1 for the rating, which basically means that an interaction has taken place. We're not interested in how high the user rated the item, because we only have so we don't know the actual value that users gave to such items. And then we have different contexts. So here we have tablet, mobile device, or a computer. In this case, there is a binary true value for the tablet. So the user accesses the system with a tablet, not a mobile device, not a computer. And like this, we have a whole list of interactions to train the model. Then we have a test data set, which basically looks the same, but is kept away from the model while training it. And then in the end, we try to predict these entries, and how good the system is at predicting these entries determines how good the system is in general. So then, let's see if I can get the terminal up. Yep. So we have a oh. Oh, I want to show you the setting as well. So there is a whole list of settings here, basically saying which recommender to use. In this case, it's a context-aware matrix factorization algorithm, but also how we evaluate the setup with a test set. We want to show a list of 30 items. We have 5 factors and 30 iterations, and for all the different algorithms, we have different configurations that we can apply. Then we have we have a jar, which is the library. We have the settings. We apply it on the data sets. The system goes to work. It shows that it has loaded the data sets. 9,000 users, 600 items, stuff like that. It shows the iterations on the algorithm. And then in the end, we got some results. They're stored in a different data set. So here we get the results, for instance, showing the mean average precision again. We can use that data, for instance, in which results in similar graphs that I showed you earlier, combining those results in the graphs that I showed you. And then the most interesting, of course, is what's resulted here in the list that user is accessing the system. In the test data set, then
regular model with adding in the different contexts, so each product now becomes a multiple products with different context?
No, so the assumption is that with a 3-dimensional model, you get more accurate results because you take into account all the different interactions between the different dimensions. So other approaches are, for instance, filtering based on, because, well, I know that a certain product is relevant in a certain context, but then you don't take into account the interactions with items that are not that relevant in that context,
Yeah,
but they might be of interest. So that's why I chose to use a whole 3D representation. And then, of course, the problem is that the algorithms have to be made useful for that case. Normal algorithms are only suitable for 2D representations. So that's the challenge then. But the assumption is that that results in better recommendations because you take all the different effects in all three dimensions into account. So, yes, another one for the mic.
Yeah, thanks. Well, you mentioned there you had 6 different data sets.
Yep.
And you mentioned for all of the 4 different contexts,
Yep.
the data sets showed different results.
Yep.
So I'm interested, what are the different data sets? What's the difference between them?
So basically it's different titles within Sanoma. So we expected that for certain data sets, for certain titles, some contexts might be more relevant than for other contexts. So for instance, we had a data set where items are really bound to a specific location, while in other data sets in normal web shops, it doesn't really matter where an item comes from. In other data set, it does matter because items are bound to a location, and we expected that, for instance, the geolocation, which was one of the contexts, would be more useful in that case. So the recommendation would be improved more by using that location there. But in the end, as I told you, that didn't turn out to be that the case, that assumption. But for all data sets, the results were improved with one of the 4 contexts, although in some cases it wasn't easy to predict beforehand which context actually improved the recommendations.
And could you try the same thing again with different data sets?
Yeah, you can basically put the algorithms don't care what the contexts are or what the data sets are. So you could, if you get the results in the data sets that, no, because, well, it didn't scale that well, so that was basically the problem. But you can get every data set and put it into the algorithm and get the results. So
okay, thanks.
Easy try out. Yes, no problem.
Final question for Bas. Yeah, what's the training time and getting it live? What?
Yeah, so that's hard. So this in particular implementation wasn't really distributed or anything. So for some algorithms it took like 2 weeks to train it, and then yeah, so that's really a problem. I tried to improve it a little bit, but yeah, it has to be scaled and it has to be implemented really in a distributed way to get it workable for the huge data sets that we have here. So that's really a problem at the moment. And in general, because there are no public toolkits for this to do this on scale, so that's a problem. No, not at the moment. No.
Okay. Well, please another round of applause for Bas.
Yes, thanks.